Guys, my name is Liad. Today I will discuss about bitwise operators which can be used to manipulate bits. So bitwise operators, firstly bitwise not operator. Bitwise not is an unary operator that flips the bits of the number. Bitwise not is nothing but simply the ones complement of a number. So it is an unary operator, that means that it works or operates on a single bit or on a single operator. So it just flips the bits of the number. So if the bit is 1, then it will flips to 0. If the bit is 0, it will flips to 1. So just ones complement. So suppose this is n equals 21. This is the binary representation of 21. We want to make the not operation of this number 21. So the not operation of 21 will be this. This is the binary representation of 21. So first one will be flipped to 0, second 0 will be flipped to 1, then this 1 will be flipped to 0, this 0 will be 1, and this one will be 0. This is the binary representation of 10. Okay, so the not value of 21 will be 10. So then AND operator, because AND, this is a binary operator. So binary operator means that bitwise AND operates on 2 bits, right? So if both bits are 1, then the resulting bit will be 1, otherwise it will be 0. Okay, so let's see. uh, Suppose value 9, this is the binary representation of 9, and 5, this is the binary representation of 5. We want to do bitwise AND of this A and B, which is 9 and 5. First of all, we have to make the length of both bits same, right? The length of binary representation of 9 is 4, and the length of binary representation of 5 is 3, right? So we have to make the length equal. So for that we have add a 0 to the left. Okay, because bitwise AND operates on 2 bits, right? So we have to make the length equal. Then see the AND operation. First the 2 bits are 1. If the 2 bits are 1, then it will be 1. Then this is 0, this is 0, so it will be 0. This is 1 and this is 0, this will be 0 also. This is 0 and this is 1, this will be also 0, because if the both bits are 1, then it will be 1, otherwise all the bits will be 0, right? So this will be 1. So then let's see bitwise OR operator. Bitwise OR is also a binary operator that also operates on 2 bits. So if both bits are 0 in this case, then the resulting bit will be 0, otherwise it will be 1. So it is the inverse case of AND operator, right? Suppose these two number we want to operate on. So we want to do A or B, which is 13 or 4, right? So this is the binary representation of 13 and this is 4. We have made the length equal by adding 0 to the left. Then the first bit is 0 and this is 1. So the OR will be 1, right? This is 0 and this is 0. So if both bits are 0, then it will be 0. This is 1, this is 1, this will be 1, because only if the both bits is 0, then it will be 0, otherwise it will be 1. So this is 0, this is 1, this will be 1. So then this is the binary representation of 13. Okay, so then let's see bitwise XOR operator. Bitwise XOR also operates on 2 bits. So in this case, if both bits are same, that means if both bits are 1 or 0, then the resulting bit will be 0, otherwise it will be 1. Okay, let's see, we want to operate on 10 and 6. We want to do bitwise XOR of A and B, that means 10 XOR 6. Okay, so this is the binary representation of 10 and this is the binary representation of 6. The both first bit of the two numbers are 0, right? So the resulting bit will be 0, because if the both bits are same, then the resulting bit will be 0, otherwise 1. So then the second bits are 1, also the same, then it will be also 0. Then the third bit is in this case 1 and in this case 0, so it will be 1. In this case the fourth bit is 0 and in this case 1, so this will be 1. So this is the binary representation of 12. So A XOR B will be 12, right? That means 10 XOR 6 will be 12. So then let's see the operations in tabularized form. This is the value of xy we will operate on, and first of all this is not operation on x, and this is bitwise AND of x and y, bitwise OR of x and y, this is bitwise XOR of x and y. Okay, first of all, if both bits are 0, in this case bitwise not of x will be 1, right, because x is 0. Then bitwise AND of x and y, we know that if both bits are 1 then it will be 1 in the bitwise AND operation, but in this case none of these are 1, so it will be 0. Bitwise XOR, in the bitwise XOR operation we know that if the both bits are same then it will be 0, so in this case the both bits are same, then it will be 0. So then let's see 0 and 1. So the not of x will be 1 because it is 0, x is 0, and bitwise AND of x and y will be 0 because both bits are not 1, right. X or y will be 1 because both bits are not 0. If both bits are 0 then it will be 0. X or y will be 1 because both bits are not same, then in this case not of x will be 0 because x is 1. X and y, it will be 0 because both bits are not 1. X or y, it will be 1 because both bits are not 0. X or y, it will be 1 because both bits are not same. Then the last case not of x will be 0, x is 1. X and y will be 1 in this case because both bits are 1. X or y will be 1 in this case because both bits are 0, then it will be 0, otherwise it will be 1. So this is 1. Bitwise XOR will be 0 because in this case two bits are same, right. Okay, we have another two operators, two bitwise operators. First of all, one of this is left shift operator. Left shift operator is a binary operator which shift the sum number of bits in the given bit pattern to the left and append 0 at the end. To do left shift operation we need two operators. First of all, the operator which on which we want to do the left shift, and another operator is how many bits we want to shift to the left. Okay, left shift is equivalent to multiplying the bit pattern with 2 raised to power key if we were shifting k bits. So suppose we are shifting value a with k bits, then the resulting left shift operation will be the a multiplied by 2 raised to power k. Okay, let's see, we want to operate on 11. This is the binary representation of 11. We want to suppose left shift 2 of 11, then it means that we have binary representation of 11 is this, right. So we will left shift all the bits to the left, 2 bits. Okay, 2 bits to the left. How can we do that? Simply we will append 20 at the beginning. Okay, we will append 20 at the beginning, then it will be shifted to the 2 bits to the left. Okay, so then this is the binary representation of 44. This is actually the same value of 11 multiplied by 2 raised to power 2. We have shifted 2 bits to the left, so it will be 2 raised to power 2, and we have shifted 11, right. So it will be the resulting value, you can check that. Then the right shift operator, another operator. Right shift operator is a same binary operator which shift the some numbers of bits. In the left shift we have shifted to the left, so in the right shift we will shift to the right. Okay, then the resulting value will be in this case divided by 2 raised to power k if we shifted k bits to the right. Okay, so suppose we will shift 11 to the right, we will shift 2 bits to the right. This is the symbol of right shift. So this is the binary representation of 11, right. If we shift 2 bits to the right, then the 2 bits to at the beginning will be removed. Okay, simply the 2 bits of the beginning will be removed, so it will be 1 0, so it will be 2. It is the binary representation of 2. Okay, so this is the same value, you can see this is the same value of 11 divided by 2 raised to power 2, where I have shifted 2 bits to the right and I have shifted 11. Okay, so this is the symbol you can check. So this was all for today. Till the next video drops, keep playing with these bitwise operators, keep practicing, and thank you for watching.